Well, good morning, everybody. Welcome to the seventh episode of our third season of Future of Urban AI webinars. Crazy day today. We have a big election result in the United States, but I think everybody's eager to get back to work and start building the future. Bear and the Urban AI team are in Barcelona at the Smart City Expo. So I hope you all are having fun and learning a lot about smart city solutions from around the world. Um, just want to recap the schedule. We have one more session that'll be next Wednesday at the same time with Tom Sanchez from Texas A&M University talking about AI and urban planning. And as always, all of the episodes from season 1 and season 2 and season 3 are now being posted to Urban AI's YouTube playlist, which you can get to with this tiny URL. And then we also have the report recapping last year's series, also available at a tiny URL. And today, I'm really pleased to welcome Weilie Yi, who's Chief Technology Officer for Hayden AI. I met Weilie probably about a year and a half ago and have been following the company's journey. As many of you know, Hayden AI is the vendor that is supplying all the bus lane enforcement cameras for New York City Transit. So this is a technology that impacts my life in a really positive way every day. They're working with lots of other cities as well and growing and innovating. And we're going to hear from Weilie today about the work that he's doing leading that. So just one other resource to point you all towards, the Future of Urban AI forecast that we drafted over the summer, have put into kind of an alpha release at futureofurbανai.org, pulling together a beta release, which will have some additional content and features that'll be released at the Urban Tech Summit on November 20th. And then Urban AI is also ramping up another phase of research and interviews that will be flowing into the Horizon Scan over the next few months. So stay tuned for more of that. But without any further delay, I will turn the stage over to Weilie, and we'll hear about using AI to help buses work better.
Okay, thank you for the intro, Anthony. Very happy to be here. It's been a great two series so far. I've watched online, so hopefully I can provide a little bit information for people to digest and have some fun. I'll share my screen right now and start my slideshow. So just a small correction. My title is VP of Data Science, but it's not CTO, but I do work a lot with our technology people. So the title of this talk is AI-powered solutions for urban transit. Here's my high-level agenda. I'm going to spend a little bit of time talk about the company itself, why we exist, and introduce the problem we're trying to solve and how we solve the problem, and then follow with some data showing if this works. So briefly, we are a 5-year-old startup company in San Francisco, headquartered in San Francisco with offices with people from many different locations. Myself work from San Diego remotely. And about the company's history, I'd like to share a small story. 5 or 6 years ago, our founder, Chris Carson, was taking a bus in San Francisco, and the bus was traveling on a bus lane. They dedicated the lane only for buses. The bus had to stop because there was a car in front of the bus and sort of blocking the movement of the bus. So the driver had to stop and took out a notepad and a pencil to write down the license plate of that particular vehicle, right? So Chris saw this and figured, oh, now it's 21st century. Why are we doing this? Why are we using pencils to do this kind of things? So that idea sort of started to grow, and the vision was, can we have machines to do this kind of things. So the driver can focus on driving safely, and the machine can watch what's going on in front of the bus automatically and be able to capture this kind of violations without disruption and be more accurate. So that's the idea of hidden AI. And we are now operating in many cities. We consider us as a leader in the market for automated mobile enforcement. We started working with MTA in New York, which is our first customer, also the biggest possible customer in our domestic market, which is a little bit weird, but we're happy to be working with them for over 2 years. And we are also in talk with many other cities around the world. So the problem we're trying to solve, as I mentioned, has to do with transit violations concerning buses, right? So that includes several categories of violations that impacting bus operation. One of them is bus lane and bus stop violations. So again, bus lanes are dedicated lanes only for buses to make sure the bus can go through slow traffic easily. So that can ensure the on-time arrival, so people can get to the bus at the right time. And bus stops are set up to protect the area leading to the bus, so the bus can probably pull into the bus stop and get people on and off the bus stop at the bus. However, if bus lane is blocked, in this case, the black car on this painted area, buses have to navigate around the blockage, making bus slower and less reliable. At the same time, because bus is slower and had to be idle and waiting for the chance to merge on into the left lane, and that's going to produce increased level of greenhouse gas emission. So there was a study put out by the National Renewable Energy Laboratory. They measured, on average, a transit bus spent 9 hours operating on a typical weekday. And 3.7 out of that 9-hour time period was spent on idle state. Idle is defined as speed less than 1 mile per hour, and engine is running non-zero RPM. So that translated to $2,500 fuel wasted per year per bus. And that's wasted fuel at the same time producing 7.2 tons of CO2 emissions. So that's both the economical problem and the environmental problem. Similarly, if bus stops are blocked, it's going to be creating a dangerous situation for people to get on and off the bus. They have to walk across the parked car vehicles. In this case, the blue Toyota car blocking a bus stop. You can see from behind the car, there's a little pole and flag saying Route 21. If you can see the letter. In this case, the bus typically have to park to the left of the parked vehicle. Passengers have to walk through the two cars to get on to the bus and get off the bus. So that's walking into traffic, very dangerous, especially if the passengers include people using wheelchair. So for wheelchair to be able to get on the bus have to be close to the curb and deploy a ramp, allowing the wheelchair to go on and off. When that's not possible, it is very hard for disabled people to get on the bus. So there's unique challenges from blocked bus stops as well. The other category of blockage, which not only impacts bus operation, but general traffic, is double parking. So double parking is when a car, in this case, this Hyundai on the right, tries to find a place to park, but there's no space left. They just stop there and blocking the traffic. Obviously, there's a safety issue if the driver has to pick up, for example, coffee. They have to get out of the car, walking in traffic. That's very dangerous. And bicycles may have to navigate around the car. It's danger for many different kind of mobility modes, and obviously it's blocking one lane and just reducing the surface shared by many other cars, slowing down the traffic. So those are the kind of problems we think this mobile solution can reduce. So talking about solution, here's an overview, right? We have the mobile computer vision perception platform. It is mounted behind windshield. It's a camera which moves along with the bus. So wherever the bus is, the camera is seeing what the driver is seeing, and the camera detects parking violations, movement violations, which is interfering with operation of the buses. And also for privacy protection purposes, we only detect objects or lanes, cars, but not people. And if we have to share some of the image to another party, for example, law enforcement, we blur the faces and the license plates, so we're not sharing any privacy unnecessarily. So here's a quick sort of demo or of how what the vision system is seeing. Let me pause to walk through the scene we're seeing. So this is a typical computer vision annotated image or video. Hopefully this nothing super weird. We have bounding boxes for each object, in this case, cars and trucks. And also we are detecting the lanes, curbs on the road. So this allows us to understand the streetscape, understand the relationship between vehicles and the road service. So that can, in this case, we are seeing many violations in terms of bus lane and the bike lane and some other cases. Here's another example. I think is different city. Hopefully, okay, yeah. So this I think is New York. Very similar situation. This the white truck was double parking, also blocking the bike lane. So hopefully get some idea of how we are, what kind of information we are processing. So everything you see happens on the edge, right? We're not shipping any video online or back to the office. We process the image on device. So we are limiting our privacy. We are making privacy protection much easier by not moving the images away from the bus. Go to next slide. Okay, so here's a quick overview of the hardware system. There are two cameras, if you haven't noticed. On the left, the smaller one is called the context camera, which is facing out and seeing what's in front of us. So that allows us to understand the physical, the spatial context, where is the curb, where are the lanes, which lane the bus is on, where's the intersection, and so on. And then there's a second camera called LPR. LPR stands for license plate reader. It reads, it faces away, faces to the right if it is in the US. When we drive on the right side, it faces to the right side and down to look at particular areas of the right side lane. And its main purpose is to figure out where is a license plate and what's on that license plate. The box we see is basically a Unix or Linux machine, very compact. We install this on the bus, so we do all the processing over there. The video is 15 Hertz, so we process the entire image 15 times a second right there on the edge. Then if you look at the second row, the most important piece of the system is antenna, right? So this is installed on top of the bus, which is responsible for getting cellular signals from LTE and getting Wi-Fi connection when the bus is back in the bus depot. It's able to do data transmission with higher bandwidth. Most importantly, it has a GNSS antenna, so we can talk to GPS and other systems for location purposes. There also a sensor fusion happening at the same time with accelerometer, gyroscope. We can fuse all the information to get more accurate measurement of location of the bus. And also we have interface talk to whatever sensor there is from the bus. For example, the rotation of wheels that help further improve the precision or accuracy of locations. So we need the location and camera calibration to be able to know where a car is located based on the relative location in the image and how far it is from the antenna. So another view of the system, you see two cameras in the middle. They have to be properly aligned, calibrated. We need a mapping matrix homography to translate one part of the we can know one car from camera A is this particular car in camera B. So when we detect a violation, we can pull the license plate from the correct car. So here's a quick overview of what our customers are seeing. If they log into our website, they can see all the violation events happening. They can do a lot of filtering. They can look at a map, look at a spatial distribution, look at when they're happening at different time of day, and check each route. So a lot of things they can do with this data. But eventually, we send each row, we package each row as what's called evidence package downstream to either law enforcement or their contractors to process this violation. So evidence package includes a short video that includes the particular time when we see violation, in this case, a bus lane violation in the middle of the white painted lane. It includes location, time, and the license plate number. So that's an entire piece of information with a lot of metadata. So if the case is being challenged in court, this is the kind of thing that the law enforcement can provide and to defend the case. Okay, so we just saw a single event or a page of maybe 10 events, but since the buses are driving around city continuously with many buses, we are seeing a lot of events throughout the day. So this is a 24-hour time lapse showing in one city how events are being picked up. So it's very fast. We can see the dots showing up. So colors are not important. We just use those to designate different route directions: northbound, southbound, eastbound, westbound. We can see during the day. Now it's 9 a.m. Things are very active, and we tend to see lower number of violations at night, and more violations during the day when a lot of traveling is happening. So this gives us a view of how spatially they are located, and also there's an association between location and time that give us some insights about where are the worst locations, where maybe additional cameras is necessary to properly enforce violations. Okay, so far I described the problem and how we are solving those. I didn't have time to go too deep into actual technology, but we have this hardware plus software solution mostly running in the cloud, on the edge, and only send out information when necessary. So the evidence package you see is a 10-second video before, 5 seconds before, 5 seconds after the time of violation. So that's only image we are sending back to the server in order to provide evidence. If there's nothing interesting in the video get deleted. So we are trying to limit exposure to imagery. So here are some early results from our customers. So MTA put out this report 2 or 3 months ago. They observed a 5% increase in bus speed. They saw less collisions in the routes where the automated system enforcing the violations. They estimated 5 to 10% reduction in emissions. Most importantly, they saw 91% of violators who got a ticket no longer commit the second violation. So that's the indication where this enforcement is changing driver behavior. So that's hopefully can produce long-term reduction in this kind of blockage and make bus go faster and more likely to be on time. Similarly, Washington, D.C. Had this report in a similar time in the summer. They saw a reduction of violation events, which went from about 20,000 per month to 13,000 per month. So if the trend continues, that's good news for a city. Hopefully that stays this way. So those are external reports from our customer, and we have no visibility in how they did the measurement, but we are interested in the same thing. So we did some internal measurement as well. So here is just give us some taste of what kind of metrics we are tracking. So on the left side, we are trying to measure bus delays or on-time arrival metric. So that's a very important metric for bus operators. They want buses to be online so people can catch the bus when it says schedule, the bus arrives at 10:30. Hopefully the bus does arrive at 10:30. So the metric we are trying to measure is 2 things. So in the chart, we have 2 bars sharing the same y-axis. So for the blue bar, we measure the delay in terms of distance. So when the bus is supposed to be arriving at the bus stop, how far it is behind the schedule, how far it is from the location of the bus stop, measured by miles. So in September, this is last year, in September, on average, when the bus is supposed to be arriving at the bus stop, on average, it is, they are 0.7 miles behind the trip. And the red and blue bar, red and green bars, same thing. They measure time. So when the bus actually arrives at the bus stop, are they ahead of time? Are they below? Are they behind? It measures number of minutes in terms of delay. So we can see in September, on average, when a bus arrives at bus stop, it is 3 minutes late. So we, in this particular situation, we deployed the automated violation enforcement solution in early October. So October is when things start to take effect. And in this particular situation, we had a 60-day warning period when during this time period, if a bus driver, if a car driver receives is observed to be violating the bus lane rules, they receive a warning but no fine. But after the 60 days, whatever violation will result in a fine. So, but we can see from October on, the delay is much smaller. And going fast forward to January, they even are a little bit ahead of schedule, which is not always good, but it's a good problem to have. On right hand side, we measure bus speed. So another city, we deployed able automated bus lane enforcement in May, and we saw the average speed per month increasing gradually. So a lot of things are happening. This is not necessarily causal relationship. We wanted to have a longer term observation to see how much impact we are generating. But so far, we like the numbers we have seen. I'll skip this into for the time constraints. So talk a little bit about privacy and data security. As I mentioned before, we are only detecting objects, not people, and we are not grabbing any sensitive information like identities, license plate numbers when it's not necessary. So if a particular situation involves many cars in the scene, only the violating car, in this case, the black car, will have its license plates detected. Every other vehicle will have their license plates blurred. If there are people around, we're going to blur their face so we're not exposing their identity. And we are GDPR compliant in EU. We did spend a lot of time. We have a dedicated team on data security. So I'm not going to dive into details, but we have a strong protection both on edge and on the cloud to make sure the data is only accessed by the correct parties, is not going to be tampered by any party during the process of this enforcement period. So that's the main part of my presentation. I probably have a few minutes left, so I'll show a final slide where we can think about any application of the system beyond enforcement use case, right? So as I mentioned, we have the vehicles running back and forth on the routes and taking video all the time, 15 hertz, 15 frames per second. We are continuously processing the view in front bus. So that creates a opportunity for us to detect what's going on in the city, regardless if there is violation. So mapping is one application we can, as you have seen from the computer vision demos, we can detect curves, lanes. So one thing we have been thinking about is to create a digital twin for the city focused on public transit. In this case, we're showing a demo which uses real footage taken by the bus, turn them into a 3D rendering of the streets. So this allows us to study how public transport is working by allowing bus operators or planners to do experiments with all the infrastructure. For example, consider moving a bus lane from one location to another location or changing the location of a particular bus stop. Does that improve or get improve traffic or get traffic worse? So those are the kind of application we have been thinking. It's long term. We're not doing that today, but that give us some idea of some other applications of the same data. So yeah, I'm super interested in that as well. That's it. So thank you for paying attention. And I think we have time for questions.
Great, thank you, Wiley. That was fascinating. I'm particularly interested in the kind of digital twin future work. We have a couple questions, comments from the audience. I'm just going to ask folks to talk come on screen and ask your question or share your comment. So Xiaopan, first.
Okay. Thank you so much for the presentation. So I've seen at least in other projects that. Oh.
Oh, I'm sorry.
Okay. Can you hear me
Are
now?
you back? Okay, good.
Yes.
Yeah.
Thank you so much for your presentation. So my question is, I've seen at least another example that use these kind of camera to capture information about the streets and put it for good use. So I wonder if they're, so the example I was thinking is B maps. I don't know if you know them. So I wonder, what's your thought on the edge of your product compared with other ones? So what is so special about this particular application? And why is it harder for other competitor to copy, for example?
Interesting. So I haven't heard about the part you mentioned. We do have competitors in the market. So whenever we try to establish partnership with the city, for example, San Francisco, we typically enter a bidding process where the cities are required to consider more than one vendor options. So we are competing with whatever technology is on the market, right? So in terms of our strengths, I think we are putting a lot of effort into making the system available and effective in all kinds of situations. One thing I didn't have time to mention is the reason we put our cameras behind the windshield is because that allows us to be able to avoid damages to the lens from objects like falling, branches or rocks in the air. And there's a design trade-off to sort of allow as much photons through the windshield and through the lens to reach our sensors, right? So that's a hardware design problem. We have a dedicated team working on problems like this to make sure we are getting very high quality of data. So that's, I think, one particular strength of our solution. And our locationing technology is very advanced. We are very accurate in terms of detecting where the buses are, and also in turn detecting where the violating vehicles are. So we have been competing with many other vendors, and so far we have pretty good track record. So yeah, the cities make the call in the end, but we have been winning a lot of those bids so far.
Thank you.
Thanks. Ariel, you had a comment. Did you want to share that in the session? If you're still here.
Hey, can you hear me?
Hi.
Yep.
Hey. Oh, thank you again. Great talk. I love your technology. I actually see it on a daily basis here in New York, so it's really wonderful. I'm interested in, I think you touched upon it in your last part about the digital twin system and the platform for assessing different scenarios. I'm interested in kind of your interface with decision makers and the way the troves of data that you're collecting could be used as sort of a predictive signal for cities, so that instead of just react to occurrences and violations in the streets, you actually be able to in advance predict some of these behaviors and take some measures in advance.
Yeah, we are taking baby steps in that direction. So the sort of long-term vision is to have this virtual copy of the city, at least in our case, the part of city where there are buses operating, right? So this vision depends on many factors. Number one, we have enough vehicles running on the streets. And now with buses, that's limiting the sort of the space we are observing. So we are actually talking about deploying the devices on other kind of vehicles, for example, street sweepers. There is unique problems to solve with street sweepers. So cases like that can expand our spatial coverage. So that's one hurdle. Number two is to collect a lot more information from the image we have. Right now, based on our product, right, we are specifically detecting violating vehicles. We are not detecting people. We're not tracking human traffic or foot traffic on the street. So in order for this simulation to be effective, we need a lot more data to enable such applications. But I think we have the sort of advantage in terms of a high frequency scan of the streets. Imagine, buses are arriving at the bus stop every 5-10 minutes during the day. That means if we have full deployment of our system, we are seeing the same bus stop 5 or 10 every 5 to 10 minutes. So whatever is changing, we can detect very easily. So one potential application of that is to detect any damages to the facility, any graffitis that's blocking the sign. So yeah, so that's some kind of more immediate applications of the data before we reach that eventual goal of having a virtual copy of the city.
Great, thank you.
Thanks, Weilie. There was a question in the chat about kind of probing a little more deeply on some of the privacy issues. One, whether any of the data that maybe isn't being transmitted to the cloud or is being redacted in certain ways, whether that is used at all in training models. And then are there any circumstances where data is being used to identify pedestrians? Because there's some potential kind of beneficial applications there around pedestrian safety. And like,
Yeah.
if not, what would be the obstacles to doing that?
Yeah. So from starting from first question on privacy. So as I mentioned before, we delete 99% of video because 99% of the time nothing is happening. So if the bus isn't operating in an area where there's bus lane or bus stop, we can potentially shut down the video processing. We're not doing that just to make things easier. So when there is a violation happening, we take this 10-second video, send it back to our server. That's going to be processed by review, and eventually some of those becomes tickets sent to the driver. So that's limiting the footprint of private information. And as I mentioned, we blur the first faces, but blur license plates if the parties are not involved. And talking about pedestrian traffic, technically we have no problem detecting those. We just don't have that classifier or detector running on the edge. That's by design. They only detect vehicles and structures in the infrastructure, the lanes, curbs, intersections, crosswalks. So yeah, so our primary product today is enforcing those rules, which doesn't need any people detection. So if there's an application, if a city wants to do something about maybe pedestrian safety, maybe any application that needs people detection, technology-wise, it's pretty easy to do, but we just don't have that mandate from our customers.
Sure. Any other questions or comments out there in Zoom land? If not, I just want to thank Weilie for sharing his time, getting up early on the West Coast on this day after a very busy night in America. Thank everybody for their interest in the topic. As I mentioned at the beginning, next Wednesday, same time, same location, will be our last session in this year's Future of Urban AI series with Tom Sanchez from Texas A&M University, talking about AI tools for urban planning. So with that, we'll call it to a close. Everyone over at the Smart Cities Expo with Uber, enjoy your time there, and hope you find some inspiration. Thank you all. Bye-bye.
Thank you.